I'm coming back to the RTD. You can see that RTD is basically the RT relation, the resistance temperature relationship is non-linear. Graphically, you can see. And as I told you on the last turn, that this RT relation, input output relationship, may be linear or it may be non-linear. Sorry. Linear means the input output relationship, the response stimulus relationship is straight line relationship, y is equal to mx plus c kind of relationship, and it may be non-linear. Most of the time you'll find it is non-linear, it is not straight line. In this case also, RTD, in case of RTD also, all these characteristics, RT characteristic curves are basically non-linear. Although platinum looks like a linear, but it is also non-linear. And any non-linear characteristic, as far as its mathematical representation is concerned, it can be represented by a polynomial of degree n. Here you can see that these characteristics in general, because till now this relationship will be, we call it is established only when the coefficients are known, alpha 1, alpha 2, alpha 3, and so on. So it is a general expression, polynomial expression for RTD. The relation between the response, that is your resistance, and the temperature. So this is the polynomial relationship. But please listen very carefully. We always want, this is the most desirable requirement, that we always want that relationship between the response and the stimulus should be linear. हाँ भाई, कोई क्वेश्चन कुछ पूछना चाह रहा है? Anybody is asking anything? जी. Any query? Any question? Should I continue?
Yes, sir.
Yes, sir.
So in this case, you see, so we want, and it is most desirable. What is the motive? That we want that the relationship should be, and for calibration, this relationship is absolutely necessary. So this relationship, we always want that the input output stimulus and response relationship should be linear, but it is not in our hand. It depends upon what kind of material you are using to make the sensor. Like if we are using these materials like nickel, copper, platinum to make us RTD, so the how this material is behaving with the temperature, resistance of the material is changing with the temperature, it is all that. It is not, you can not, human being cannot modify the behavior of the material. Means in its pure form. Obviously, if you are adding something, or you are doing some heat treatment or something like that, or some electrical mechanical treatment, then there may be certain changes. But as such, in pure material, it is not possible. So, and what is the motivation? If your relationship is a straight line relationship, linear relationship, then minimum number of data points are required for calibration. Are you agree with it or not? So if it is straight line, then only 2 data points are required. And if it is beyond that, if it is non-linear, then n number of data points are required. Right? So this is what is the motivation, what is the advantage, because calibration process is slow as well as is costly. It makes the instrument costly. So this is why we always want. And you see, it's very important thing I'm talking about, and I want that you all people, whoever is present today, should try to understand it. And if you are not able to understand any of the point, any of the concept, then you try to, it means you can ask. You're free to ask if you are having any confusion. So here in this case, what we do, the requirement, the linear uh, response, and whatever I'm discussing here, if I'm making any general comment about the calibration, it is for all the instrumentation systems, including your RTD. So the requirement of a linear relationship calibration expression, calibration curve is so tempting, uh, be- that even if your sensor is not sensor characteristic is not straight line, we approximate it by a straight line like this. You see here, the sensor characteristic is non-linear. This is the actual sensor, how sensor resistance is changing with the temperature. But what we did, we approximated it by straight line. We approximate, and whatever the popular expression you all are aware of about the RTD, that RT is equal to R naught 1 plus alpha delta T, is basically a approximate expression, not the exact expression. So what we did, we took only first two term of the characteristic expression, first two terms, and it is a linear approximation of the actual characteristic. This is your actual characteristic. So, and then we want to, so that's what I had written here, approximating actual nonlinear characteristic of RTD by linear, and this particular approximation, which is called linear approximation, is not confined only to the RTD. It is tried for all the sensors. What is the next, means next part of the story that I'll take up right now? I'm approximating the RTD characteristic actual by a straight line, and the straight line equation is this. What this is the actual characteristic. So what is the meaning of it? Meaning of it is that although your RTD resistance is varying with respect to the temperature to which it is exposed in this fashion, but we'll make the measurement by this curve, straight line, by this equation. Okay, so many times you will find obviously that measured value is different from the true value. You take I'm giving you one example. Like if we talk about, if resistance is this much, so you see this is the actual temperature, and this temperature will measure, because we have approximated it. We'll use this equation. Your scale is calibrated with this equation. So obviously there is a error between the measured value and true value. This is the error. This is your error. Now this error is called nonlinear error, or anyway it is an error. At this point of time it is an error. You consider it as an error. So this error will have certain value. Now if this error, means we will try to find out the maximum deviation within the range. Means suppose this is the range for which you are using this straight line, this equation, because if you'll change the range, then your alpha naught value, coefficient value will change. So in this case we are using this range. In this range, suppose this is the maximum deviation throughout the span, this is the maximum deviation. So this maximum deviation, if it satisfies our accuracy requirement. Now what is accuracy? Suppose we want that our result should be, measurement should be within plus minus 1% of the true value. And now if we, delta t, that is the maximum error in the span, is suppose plus minus 0.5%. Plus minus 0.5%. Our requirement is plus minus 1%. Then this is fine. We'll carry on with the this particular straight line. Although it is not accurately representing the characteristic, but that's why it is called linear approximation. And if suppose your requirement, suppose we want 0.5% and error is 1%, then obviously we won't, we will go for the, we'll take up the higher order expressions, and then it will be called quadratic approximation or cubic approximation, like that. So this is what is done in calibration. Now I'm coming back to the linear approximation. Now we want to establish the relationship of linear approximation, linear relationship between input and output of the RTD. So this equation is the basis equation. So obviously, once your coefficients are known, your alpha naught is known, then you will say that this relationship has been established. How it is done? So we have written, you see, we have written it in terms of alpha naught, this equation. Other way around we have written. So if you look on this expression, you will find basically the alpha naught is fractional change in resistance per unit change in temperature. And if you look at this part, this is nothing but the slope of the straight line, slope of the your approximate straight line. So finally, that's what I had written, 1 upon RT naught into slope of the straight line. So ultimately, you can take any 2 points on the straight line. 2 data points are required. That's what I'm saying. At any 2 points on the straight, any 2 points, because slope of the straight line is constant. Although slope of the, so if I'm taking any 2 points and then we are putting it here, then we get the alpha naught. Once alpha naught is known, then we'll say that the calibration is done and our input output relationship is established. By measuring the RT, we can measure the T accurately, whatever accuracy you are claiming. Okay, and when, if this accuracy means whatever accuracy you are getting, measurement accuracy, if it is satisfying the desired accuracy, then we'll go ahead with this approximation. And if it is not, then obviously we have to go for the non-linear approximation. So if anybody is having, this is a very important topic, and although I discussed this calibration with respect to the RTD, but this particular concept and this particular thing is applicable to all the sensor-based systems, to all the instrumentation systems. Okay. So if you are having any query regarding it, whatever I discussed about the calibration in general of the RTD and linear approximation. And linear approximation is tried for all the sensors. This is also the generalized thing. जी, आपको कोई क्वेश्चन पूछना है तो पूछ लीजिए. If you don't have any question, then I'll move ahead. I took one example, whatever I explained.
सर एक्सक्यूज मी सर.
जी बताइए.
सर आपने जैसे बताया था डेल्टा टी जो है वो एरर आ रहा था लीनियर और जो आपका रियल में जो आपका कर्व है और लीनियर कर्व है,
जी जी,
वो दोनों के बीच में एरर आ रहा था डेल्टा टी.
जी बिल्कुल सही.
लेकिन सर एक्चुअल में से डेल्टा टी जो है वो आपका इनिशियल टेम्परेचर से जो फाइनल टेम्परेचर है.
Don't get confused with this and that. You can make it del T. Don't get confused. That T, delta T in the expression is not this T. This is T is basically error. Don't get confused with that. No?
Okay, sir. Thank you.
This is not that delta T. Okay, this is your error. Your actual temperature obviously is something, and you are measuring it is something. Like actual temperature is because of this approximation, because of this approximation. Your actual temperature may be, suppose, around, you are measuring, suppose, room temperature, and your actual temperature is around 35 degrees Celsius, but you are measuring, suppose, 35.5 degrees Celsius. I'm giving one example. So this difference of 0.5 degrees Celsius is called error, and it is because of the linear approximation. Now, if you want, suppose you want that your result should be within plus minus 0.5 degree. So this kind of up to this much error, you can say that this is fine, this approximation is fine. But suppose you are saying that I want that it should be around 20.25 degrees Celsius, error is tolerable, not beyond that, then obviously this approximation will not work here. Then you have to, the next step will be, you have to take the next term also into it, because you see, this relationship is actually non-linear, so it will be better represented by the non-linear characteristic, non-linear equation. So when you will take up the next term, then it will be called the quadratic approximation, and your quadratic approximation is obviously non-linear approximation. So, but I'm not saying that it is the ultimate thing. Even the quadratic approximation may also have error. It is not matching with the curve is not quadratic in nature, it may be cubic in nature. So but in any case, it will give you the better matching, so the error will be less. So this kind of thing is done. Okay, Amai?
Yes, sir. Thank you.
Now you see, you solve this problem, thing will be more clear to you. Find the linear approximation of resistance versus temperature between 60 degrees Celsius and 90 degrees. By what percentage? So first of all, I'm concentrating on this part. So here you can see that so many data points. These are the data points. Although there is a redundancy, we don't need these many data points. But any case, experiment is done, and then these data points, suppose very accurate kind of data points, because these data points we are using. So between 60 degrees Celsius, this is the range. Whatever calibration that will be done, it will be valid for this range only. Now suppose if you are changing the range, instead of 60 degrees Celsius to 90 degrees Celsius, you want to use it between 50 degrees Celsius and 80 degrees Celsius, then whatever calibration we have done, alpha we have calculated for this range will not be valid for that range. It will change. Then you have to again recalculate. So that is called recalibration. So here anyway, so for this range we want. So generally what is done, we take the midpoint of the range. So in this case, it is 75 degrees Celsius and corresponding value. So we are taking it as a R naught, as a T naught, and R naught. So that's what here, T naught and R naught, T naught or R naught. So I put the values here. So we have to calculate the alpha, and you know the alpha formula we are already aware of. This is the slope of the straight line. Whatever straight line means, you are assuming that the straight line is passing through these 2 points. This, when you will draw it, so it will give you something non-linear character like this. Now we are approximating, suppose this is your 60 degrees Celsius and this is your 90 degrees Celsius. So we'll make a straight line passing through these 2 points. So using these 2 points, we can calculate the alpha value. that this is the formula, and 1 upon RT naught, this is. So this we calculated alpha, and this is the alpha. Now you can see that once we are aware of alpha, we can say that calibration is done, and we know a relationship between RT and T has been established. You see, this is a straight line equation between resistance of the your RTD and the temperature to which it is exposed. So this calibration is done. Now the second, by what percentage do the predictions of the linear approximation vary from the actual values? That's what I was saying, that error. Here we are talking about the error. So actual resistance at 60 degrees Celsius is this, and actual resistance at 85 degrees Celsius is this. But it is not necessary that that approximated value will be same. That's what. So for here I had written calibration is done for the range of 60 degree to 90 degree Celsius. Now I calculated with this equation, I calculated the value of resistance at 60 degrees Celsius. This is coming out to be 107.1 ohm, whereas actually it is 106 ohm. So error is 1.04%. And at 85 degree, the value is 112.3 as per the equation, calibration equation, and actually it is 111.7. So the error is 0.54. Suppose this for 60 to 90 degrees, suppose this is the maximum error. This is the maximum error. So manufacturer will say that with this calibration, the maximum error is plus minus 1.04% you should expect. Maximum, not the minimum, maximum. So now if you are going to purchase this meter, this thermometer, for measurement of temperature, and if your accuracy requirement is plus minus 1%, then there is no issue. But if your accuracy requirement is plus minus 0.5%, so obviously this calibration is not suitable. And if you are a manufacturer, then you have to, the customer's requirement, then you have to go for the next stage, that is called quadratic approximation. And obviously again we will try to find out whether with the quadratic approximation, obviously in quadratic approximation your maximum error will reduce. That is for the sure. It won't be worse than this or even equal to this. It will be better than this. But it is matching the requirement or not, that is another issue. So this is how things are done. Meters are calibrated, and these are the requirement. This is the process. All these things is done. If anybody is having any query regarding this numerical problem and the concepts I'm trying to convey through this numerical problem, you can ask, please. भाई कुछ तो बोलो तुम लोग.
So got it.
You people got it. Okay. Now signal conditioning. So you see, again we are using I told you that this bridge circuit is considered as one of the best circuit for signal conditioning of resistive sensor. So your like a strain gauge, your RTD is also a resistive sensor. So your Wheatstone bridge circuit, in this case your RTD is converting the temperature into the resistance, and it will convert resistance into the change in resistance in the voltage. So two stages are here. So your RTD is one stage, your temperature is converted into resistance, and your bridge is another stage. It is converting the resistance into the voltage. So finally your temperature, here input is your temperature. So finally your temperature is converted into voltage. So suppose at the initial temperature, all the resistances are equal, R1, R2, R3, RTD, all equal at the room temperature, suppose. And now if there is any variation from the room temperature, so your this voltage will be 0 at room temperature, and if there is a variation in temperature below or above the room temperature, then you accordingly you will get this voltage. As you know that RT, you see how things are done. RT is equal to R naught 1 plus alpha naught delta T. This relation just now means we are taking this linear approximation. Or by the matter of fact, any expression we require, whether it is a linear or non-linear, we require this kind of relation. This is the integral part. Now I had written delta R change in resistance with the change in temperature. It is RT minus R naught, RT minus R naught. So it is equal to R naught alpha delta T. As you know that in this case, in bridge case, the voltage sensitive bridge in deflection mode, the output voltage, the voltage across the detector arm is equal to V upon 4 into delta R upon R. We have derived this expression in the first unit. Again, in the case of strain gauge, we have studied this. Now this we replace this delta R by this expression. So now you can see that the voltage, output voltage, whatever we are getting here, it is related to the temperature. It is related to the temperature, and all other things are basically coefficients. These all are coefficients. So you can see that the voltage will vary as per temperature, and with this expression you can find out, if you know the voltage, you can find out the temperature. So this is fine, all of you?
Yes, sir.
Yes.
Then if you go to the market, actually you'll find the lead resistance is one of the issue. Lead resistance is one of the issue in all resistive sensor, not only in RTD, because generally you will find that the long leads are used, because this circuit in the industry, this circuit and will be in the control room, and your sensor will be at the shop floor somewhere. Certain processes are there, you are measuring the temperatures, and then there are the long wires which is connecting sensors to the control room, where these circuits are implemented, and you are having dashboard and everything, all the meters are over there. So this lead, obviously lead is exposed to the environment also. So the lead resistance is itself is an error, and this error is dynamic error, because your lead is exposed to the environment, hostile environment of the industry, and as the temperature and many other things will change, lead resistance will. So lead resistance itself is an error, and then this error is also basically varying with means it is not constant type of error, it is a variable error. So this so lead resistance compensation is one of the issue in resistive sensors when you are using it. So different type of lead resist, different type means 2 wire, 3 wire and 4 wire RTDs are there in the market. 2 wire, obviously there is it is not possible to compensate any lead resistance, any means provide the compensation for lead resistance, but in 3 and 4 it is possible. We make the connection in the bridge circuit different way. So here you can see that this is your RTD. It is having 4 terminals, 2 at one side, 2 at the other side. Here in this case you can see that you are having one terminal at one side, and the other side is two terminals, 2 leads are there, and they are basically connected in a particular way in the circuit. Here you can see that this is the 3 terminal RTD is used, connection is used this way, just to avoid the effect of the lead resistance on the final measurement. Here it is 2 wire. Here in this case it is not possible to compensate, but here you can see the changes, connection change. And here this is 4 terminal, that voltage is measured These are the two are the potential terminal and two are the current terminals. So potential terminals are very close. So lead drop across the lead is not counted here uh, when you are measuring the resistance. So that's why. So this is how compensation is done. So you can look upon it, how it is done, what is the expression, that is out of the scope of your course. But at this point, you should know that many type of means with the different you can say that wire RTDs are available in the market, and these wires, if you are having more than two wire, they are basically for implementation of lead compensation when it is connected to the measurement circuit. So this is what is the main issue, main thing. So here we finished the RTD. We discussed many things about the RTD. If you are having any query regarding resistance temperature detector, what is a resistance temperature detector, what should be the attributes of the material, and what is your temperature coefficient of resistance, and what is the nature of it, and then calibration in detail we have discussed, and then signal conditioning also we have discussed. Then we talked about the lead resistance compensation. So this is all we are supposed to cover. If anybody is having any query regarding RTD at this point, you can ask, please. Anyway, then I'll go. I'll take up another sensor. Now I'll take up another sensor. It is thermistor. Thermistor. Anybody knows? Does anybody know thermistor? जी, कोई जानता है थर्मिस्टर क्या होता है? नहीं जानता को. Anyway.
No, sorry.
जी, आपको मालूम है?
नहीं सर, नहीं.
नहीं मालूम.
Sir, whose resistance is dependent upon temperature?
जी, whose resistance
is dependent upon temperature?
Correct. But then the same thing is RTD also. RTD's temperature resistance also depend upon the temperature. By measuring the temperature resistance, we measure the temperature. What is the difference between? You're correct. Whatever you said, it is correct. Perfectly all right. But how come this means? Because same thing is about the RTD also. We have studied just now. We finished that topic. So how this thermistor is different from the RTD?
So here we are using the semiconductor.
Correct. This is what is the main difference. That RTD is made up of conducting material, and means when we are discussing the RTD, which is made up of conducting material, then it is the obvious thing that should come in our mind, that semiconducting materials are more sensitive to the temperature. So why not we should use the semiconducting material instead of the conducting material? So this is the answer for that thought, you can say. So thermistor is basically a resistive sensor like RTD, and it is unlike RTD. It is made up of semiconducting material. And when it is made up of semiconducting material, so obviously your temperature coefficient of resistance will be negative, because in semiconducting material it is having a material property that if you will increase, because there is a physics behind it. If you'll increase the temperature of a semiconducting material, then its resistance decreases, and if you'll decrease the temperature, then resistance increases. If you'll increase the temperature, then resistance decreases, and will decrease the temperature, resistance increases. Both of changes in opposite direction. Whereas in case of conducting material, the situation was different. Over there, the temperature coefficient of resistance was positive. So when we'll increase the temperature in case of the RTD, your resistance will increase, and when you will decrease the temperature, your resistance will decrease. But here thermistor, because you must have studied the band gap theory in case of semiconducting material. So there is a gap between the conduction band and the valence band. Whereas in case of conducting material, there is no gap. Your valence band and your conduction bands are overlapped. So in the case of conducting material, there are a lot of electrons are always available. Free electrons are always available for the electrical conductivity. But here in this case, it is controlled in case of semiconducting material. So actually what happens in this case, as far as its behavior with respect to temperature is concerned, when we heat up the semiconducting material, so the electrons which are available in the valence band, they gain the energy from supplied thermal energy, and it crosses the band gap, and it goes into the conduction band, and means it will be free. It will be available now. Once it reaches to the higher conduction band, then it is available. It is free now. It is not attached to the any bond of the atom, and it is free, available to conduct the. So obviously its conductivity will enhance, its resistance will decrease, and otherwise when you are cooling it down, then whatever electrons with the higher energy available in the conduction band, they will lose their energy, and they will they will be acquired by some atom, and they will be part of the they will come back to the valence band. So this is how, because of this reason, your conduction getting enhanced when it is exposed to the high temperature, and because more and more electrons are available in the conduction band, and when you are cooling it down, then it is losing its energy, coming back to the valence band, and less number of electrons are available for conduction, so its conductivity decreases. Or when conductivity is increasing, means its resistance is decreasing, and when conductivity is decreasing, means its resistance is increasing. So this is how this material, and it is very sensitive. It is means much more sensitive than your RTD. So this is how thermistor, what is thermistor, and what is its basic behavior with respect to temperature, and what is physics behind them, that all I tried to explain you. Now a few more things. So the temperature coefficient of resistance of thermistor is found to be large as ever. So this is you can say that superiority of the thermistor over the RTD, that its sensitivity means temperature coefficient of resistance means sensitivity. You are already aware of this term and what it is. So this is temperature, having better temperature coefficient of resistance in comparison to the RTD. So this is the advantage. So what is the advantage of what is the significance of having a large value of the temperature coefficient? That is here given here. That is obvious also, that it is possible to measure the small change in resistance. So if you are having a choice in certain application, you want to detect a very small change in temperature, then obviously your thermistor is better sensor than RTD, although both of them are resistive sensor and thermal sensor, both of them. So this is how sensors are selected basically. So and obviously when there is a large change in resistance, then not very sensitive temperature detector is required, then we go for the RTD. This is how But in any case, even if there is a large change in temperature, if you are not having RTD or thermistor, but thermistor is having one very severe limitation if you compare with the RTD, and that's why its use is limited. So thermistor exhibits very high nonlinear RT characteristic. So this nonlinear RT characteristic is basically a big issue with the thermistor, and that's why it is not very much popular. It is not as popular as your RTD, although your RTD is not as sensitive as thermistor, but it is having your RTD is also having nonlinear relation that I told you, but it is not as nonlinear as thermistor. Thermistor is having very highly nonlinear characteristic, severe, and the issue remains same. Means here in this case, in case of thermistor, you are having a very exponential kind of RT nonlinear, this kind. And if you are approximating it by a straight line, then obviously you can see the deviation is very high, and it will give you large result, large error, and that's why it is not this is not a very favorable thing. So that's why, as I told you here in this point number, the second last point, that it is used not for the large ranges, it is used for the small ranges. When it is used for a small range, like it is used, suppose, for this small range, instead of that much large range, if it is used for this small range to detect the small change in temperature, so obviously your nonlinearity is not that much pronounced. It is this much, and we can very easily approximate it by straight line, and we'll have small deviation. So this is how nonlinearity of the thermistor is handled. Okay, so this is one of the reason that thermistor is not very popular. It's RT character. Otherwise, it is very sensitive. It is much more sensitive than the RTT, but its RT relationship is nonlinear, highly nonlinear. So this is what is means what I want to share with you about the thermistor. If you are having any query regarding whatever I discussed about the thermistor, you can ask, please. Pros and cons of the thermistor as a temperature sensor I discussed. Okay. Now this is the popular RT relationship. Again, I'm telling you, here also we require a relation which basically relates the input output of the sensor, means the response and the stimulus of the sensor, and this is one of the expression, calibration expression. It relates the resistance with the temperature. And here beta is basically, and here temperatures are in Kelvin instead of, in this expression, R is in ohm and T is in Kelvin, and your beta is basically a material constant. Can anybody tell what will be the unit of beta? By looking on the expression, can you tell?
Kelvin.
Kelvin. So this is basically a constant, and its unit is in Kelvin, and it is material to material. If you are using different material, the beta value will be different. And this is a typical thermistor characteristic is shown here, that you can see that it is an inverse as well as it is a non-linear, highly non-linear. So if you are approximating it by a straight line like this, so obviously error will be very high. But if we are using a small span, like to detect a small temperature span like this, so this nonlinearity will be comparative, and we are approximating it by a straight line. Anyway, so the deviation will be less. So this is how nonlinearity of the thermistor is tackled. Other things we'll discuss on the next turn as far as thermistor is concerned. So I'm closing today's discussion here only. If anybody is having any query regarding thermistor, you can ask. Anyway, respond your roll call now. Roll